tells about the carbonyl chemistry. Okay, so carbonyl chemistry means that chemistry of carbon double bond. Okay, so this carbon double bond. So first understand the different functional groups that have the carbon double bond oxygen. So first one, if you have carbon double bond oxygen and hydrogen, okay, and this side could be hydrogen or carbon. So this is called aldehyde. Okay? In functional group, aldehyde, and this is ends with the nomenclature al, ALL. Okay. So like if it is methane, so it is methanol, from methane, one carbon, this will be called methanol. In common it is called formaldehyde. And if it is two carbon, then ethanol, and so on. Another one, if both sides you have carbon, okay, no hydrogen with the carbonyl carbon attached, then it is ketone. Ketone, and in nomenclature it ends with one, ketone, like O-N-E, one. So like if three carbons, you need to have at least three carbons to make a ketone, like this one. Generally this molecule is known as acetone, very common compound. But three carbons alkane is a propane. So from propane, this will be called propanone. Propanone. Okay. So it ends with O-N-E. Okay. The third next functional group that contains carbonyl is carboxylic acid. Carboxylic acid. Okay. So carboxylic acid, this is in nomenclature it ends with oic acid. Okay, carboxylic acid. So it will have a carbonyl and OH. Another one, this OH is removed by halogens, okay, mostly chlorines. In some cases, fluorine and bromine, they are not very common. This is called as acid halide. Acid halide. And this ends with OL halide in nomenclature, or IL, just YL. Okay. So if so this is not very common, but yeah, we'll see some reactions. Okay. Next functional group is the anhydride, acid anhydride. Okay. So these are the derivatives of acids. So when two acids combines by removing a molecule of water, then it forms acid anhydride. So acid anhydrides they end with oic anhydride in nomenclature. Oic anhydride. Okay. So another, this is not common, and you guys will see this one is more in biochemistry. Okay. So this is that, this is called, here you see acyl group, acyl phosphate. So the reaction of this we will not talk in chemistry, okay? But these are very important for biochemistry. So you should have some idea about this. So it ends with ill phosphate. Okay. Another one is very common that has the carbonyl functional group, that oxygen and attached with R group or carbon attached. So this is ester. Okay, it's a very common, and we'll talk about this one. And this one ends with in nomenclature O8. Okay. Another related to this, remember this one here. O8 when they are just cyclic, okay, they attach with this one. See here, this carbon, suppose here it attaches this cyclic structure, oxygen attached with carbon, and they are cyclic. This is called lactone. Okay, so this is remember this is the lactone. So if you replace oxygen with sulfur, okay, here sulfur. So then it is called thioester. Thioester. Okay. And here you see these esters, they end with O8. So thioesters will end with thio-O8. Okay, thio-8. Okay. And the last and one of the most important functional group is the carbonyl that has nitrogen attached. Okay. This nitrogen can have hydrogen attached or another carbon. So this is called amide functional group. Okay. And it ends with amide as well. So same amide functional group ends with amide. Now this amide, if it is cyclic, okay, see the nitrogen is attached with this carbon like ester. So ester, when it is cyclic, it is called lactone. When amide, it is cyclic, it's called lactam. Okay, so this is this lactam. So this is these are the functional groups, different. All we talk about that has carbonyl functional groups. So these are how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So you should know what in terms of nomenclature they are important, and then we will talk about the reactivity. Okay, now let's talk about the nature of the carbonyl compound. So this, see, there is a carbonyl functional group is here, just say carbon here. Okay, so oxygens, they have a lone pair of electrons, 2 lone pairs, and oxygen is electronegative, so it withdraws the electron pair, so it will have delta negative. Okay, and the carbon will get delta positive. It's a very basic but very important to understand this one. So what Or another, if you will write the resonating structure, see, oxygen is electronegative. It can withdraw completely the pi bond. Okay, so it can form O minus negative charge, and carbon will get positive charge. If you have, let's write two more bonds like that. Okay. So what is the nature here? See this oxygen in both the structures, it has lone pairs of electron, so it can react with a positive charge, electrophiles. Okay, so it can react with electrophiles. So oxygen is the nucleophilic in nature. Oxygen of carbonyl is nucleophilic in nature because it can react with electrophiles. Okay. On the other hand, the carbon, see, you have positive charge here or here at delta positive charge. It means it can react with nucleophiles. So both has opposite character. So that's why carbonyls are very reactive. They can react with electrophiles, and they, as well as they can react with nucleophiles, both. So that's why their reactivity, so they show lots of reactions. Okay. Now another very important thing here, you guys see this one. See, if these two groups attached, they are carbons mostly. If they can donate electrons, okay, they can donate electron. If they will donate electron, means what will happen? They will neutralize this charge on carbon. Okay, electron donating, it will neutralize the charge on carbon. So if they when they will neutralize, the charge will be neutralized, then it will not react with the nucleophile easily, or it will not react at all, or it will not react easily, because here less charge or no charge on the carbon. Okay, so electron donating will reduce the reactivity of the carbonyl carbon. Remember this one. And on the other hand, electron withdrawing groups here, okay, electron withdrawing groups, what they will do, it will increase the positive charge, that will attract more nucleophiles, means it will increase the reactivity. Okay, so this concept you guys remember very important. Okay, so these carbonyl groups, they go certain characteristic reactions, so that we will talk one by one. And then so try to understand the mechanism, do lots of practice for this mechanism, because these reactions, 3-4 reactions, as I said, in next 5 chapters, almost everything remaining in organic 2 will come again and again. Okay, so first reaction is nucleophilic addition reaction. Okay, nucleophilic addition reaction. So what does it mean? That the addition reaction is started by a nucleophile. Okay, the same like this one. See here, what will happen if there is a nucleophile? If you have here the carbonyl group and there is a nucleophile. So what will happen if there is a charge on the nucleophile? It will go to the carbon. Okay, nucleophile will always go to the carbon. It cannot go on oxygen, and the pi bond will move on oxygen. So here you see the carbonyl carbon has sp2 hybridization. After the addition of the nucleophile, oxygen will get negative charge and nucleophile will attack. Now this carbon is sp3 hybridized. and tetrahedral. Okay, first it is planar. Now it is sp3 hybridized and tetrahedral. Now next step, this oxygen negative charge, it will take a proton from acid. Okay, acid mostly many cases just in water intake, it will take a proton and this will give this product OH nucleophile attached. This is the common reaction. We have already done this one many times and we will again do this reaction. Okay, so what is the reaction we have done? Anybody can tell? This type of reaction, nucleophile reacting with the carbonyl. See, I gave you guys many examples. Let's say the carbonyl is formaldehyde, okay? And you react with Grignard reagent. So what is the reaction? So what is this one? R is a very good nucleophile. Okay. So this undergoes nucleophilic addition. So this is the classical example of nucleophilic addition. And it forms HHO minus. And here the counter ion remains that magnesium plus with Br. And then when we work up this one with with acid, aqueous acid, this takes the proton and this one. Okay, so RCHHOH. Okay, so all the Grignard reaction you guys should know. They are in this category. Okay, so in the next quiz, I can ask any Grignard reaction. Okay, so review the Grignard reactions we have done so far. Okay. So this is the example of nucleophilic addition reaction. Okay, another very common example of nucleophilic, I'll give you one more example to you guys. Just let's say this is the carbonyl and the nucleophile here, let's say nitrogen. Okay? Nitrogen and this NH2, sorry, NH2 here R and H. So Grignard reagent has a very strong nucleophile carbon. No, the nucleophile is nitrogen. Here it's different. So it will react like this. Okay. So what will happen? So R, carbon attached with R, oxygen minus, nitrogen came, and nitrogen has 2 hydrogen and it has R prime. Just let's write R prime to distinguish. Now nitrogen, see here it's neutral. It gave the lone pair to make a bond, so it will get positive charge. Okay. So here now that one of the hydrogens of this nitrogen will break off and it will move on O minus. So ROH it will be. And then you have another hydrogen and then nitrogen here and R. You see, the positive charge on nitrogen will be neutralized because the bond pair of nitrogen hydrogen came on completely to nitrogen. Okay, so this is the product this will form. Okay, So this nitrogen has a lone pair of electron, okay? So here you see on the same carbon, sp3 hybridized carbon, okay, nitrogen and oxygen, which one has a higher electronegativity? Oxygen has more, oxygen is more electronegative. So more electronegative means it will leave faster, easily. Okay. So what happens? This one will come here and this will leave. Okay. So see Grignard reagent, see the product in Grignard reagent, carbon bond formation. In that, oxygen will remain intact with the product. But here, because nitrogen has a lone pair, it can donate. So OH, it leaves. So what will happen? You'll get R, C, R, double bond, nitrogen, and here R, non-nitrogen will get again positive charge. Okay. So the solvent here or the OH minus that formed or another nitrogen can take this proton and this will go this. Okay. And the product will be RRC double bond NR plus H2O. Okay. So what is the function? What is this functional group? Carbon nitrogen double bond. Anybody remember from organic 1 to organic 2? Carbon nitrogen double bond is called imine functional group. IMINE, imine functional group. Okay, so this is the final product. So this is slightly different. Okay, see here see the difference of Grignard reaction and this reaction. Grignard reaction will stop like this here. Okay, after adding to the carbon and then taking proton, it will stop. But with nitrogen, it will go further to remove water from the system and it will produce an imine. Okay, any question? So this reaction, and remember another thing, these reactions steps are reversible. It can go back as well. All are almost reversible and can go back. So these are two examples of nucleophilic addition reaction. Another important is nucleophilic acyl substitution. Okay, nucleophilic acyl substitution. So here you see nucleophilic acyl substitution. So what happens, suppose if you have carbon O, carbonyl group, it is attached with Y. And what is Y? Y could be mostly in this case, okay, is halogens, mostly chlorine or oxygen. Oxygen with attach something. Oxygen could be here in the form of acid or oxygen can be in the form of ester or anhydride, any form. And also nitrogen, amines. Okay, why? So anything that you can say has higher electronegativity than carbon. Okay, here. So what happens then? This leaves acyl substitution, means it is substituted. Okay, so that's why this reaction called nucleophilic acyl substitution. This here, this Y of the acyl group is substituted by a nucleophile. So what will happen? Suppose if there is a nucleophile, the nucleophile will again react the same way here. Okay, with this one. So this will be RO, okay, minus the nucleophile and Y. See this one here. Now here this O minus you see and Y. So here oxygen minus is electron donating, O minus, because of the negative charge, very high electron density. Okay, and Y is a leaving group. Here Y behaves as a leaving group. Okay, and oxygen as a electron donating group. So what happens here? You can say oxygen pushes and Y pulls off by itself. Okay, so what happens? The one of the lone pair will come back here and Y will leave. So the nucleophile substitutes the that leaving group Y. So the product will be a carbonyl attached with the nucleophile. Okay. So this reaction again we have discussed previously, if you guys remember. Again, that is the reaction of Grignard reagent with an ester. Okay, exactly the same mechanism. See, if you guys remember, I gave you guys this example. Suppose if you have this one, ethyl benzoate, okay, this ester, and you take a Grignard reagent. I will give you guys a specific example, methyl magnesium bromide. Okay, here methyl kind of negative charge, so it's a very strong nucleophile. So the nucleophile reaction, what will happen with the carbonyl? See, this always the nucleophile will go to the carbon and the pi bond will move on oxygen. So here you will see this is the reaction. O minus, you have that ester here and CH3 here. Okay, and magnesium bromide will be as a counter ion. Here magnesium as a positive charge. Okay. So the next step, as I said, here this ester, this OET part acts as a leaving group. Okay, and here this negative charge on oxygen, it acts as a donating group. It pushes out the ethyl group. Okay? And this bond will break off on oxygen, will go on oxygen. So what will be the product? So here you have the phenyl, carbon attached, CH3, and the ethyl O minus left, and magnesium bromide will go with this. So substitution, see here the methyl substituted this ethoxy part. So that's why it's called nucleophilic acyl substitution. So it's one of the very common reactions you will see, okay? Another example I'll give you guys, if you have, suppose, let's say, if you have acetyl chloride, okay? And you take an amine or ester, anything you can take. Alcohol you take, okay? Ethanol. And with this reaction, you need to have a base, okay? Generally, we take pyridine as a base. Okay? So I will show you guys in a short way the mechanism. So pyridine will take this proton of OH. So this becomes more nucleophilic. And this will react again with the nucleophile carbon. The pi bond of will go same on oxygen. See, all these reactions have the initial same mechanism, okay? So you have this CH3O minus, you have attached that Cl, now the oxygen is coming, okay? Sorry, CH2 and CH3. Can I say this one? So this is the reaction. And here, what you will have the other byproduct. I'll write here this pyridine that took the proton, it will get a positive charge. Okay. Now see here, halogens, they are very good leaving group. Here it behaves fluorine as a leaving group, and O minus it's as a donating group. It donates electron. So will go this, and this Cl minus will leave. Okay. So what will be the product now? So CH3, CO, O, CH2, CH3, and ester. So the ethyl group from ethanol, it substituted the chloride, and the chlorine will go with pyridinium chloride. Okay? Here, like pyridinium as a counter ion, it will go. That's why we need to pyridine. Actually, it scavenges HCl, the byproduct. Okay, so this is the example of nucleophilic acyl substitution. Okay, any question? Okay, the next one, now if there is a carbonyl compound that is called alpha substitution. Alpha substitution. So if you have a carbonyl carbon, this is a functional group, okay? Remember here the example. The carbon attached to the functional group is called alpha carbon. Okay? We'll take the example of simple acetone, CH2, CH3, C. Here I'm writing the H separately, okay? So if you take a strong base, okay, strong base, let's say sodium hydride or lithium diisopropylamide, LDA. So what will happen? So this carbon will call alpha carbon, okay? Remember, the carbon attached to the functional group is called alpha carbon. Next carbon will be called beta carbon. Next carbon will call gamma and delta and so on. So alpha, beta, gamma, okay? Mostly we'll talk about these, okay? So, so this is one of the nomenclature type thing that frequently we use. So this strong base can take this hydrogen. Okay. So what will happen? This CH2O, here we will have CH2 minus. Okay, this negative charge. Formation of this negative charge is very easy. Why? Because this is resonance stabilized. Okay, so this is in conjugation with the carbonyl group. So it will be O minus double bond CH2. Okay, so this is the resonance. Now this as a nucleophile as a whole, okay? Here you can see this is a nucleophile, or here also this one when it will come back. So if you take an electrophile, okay? Let's say I will give you guys a real electrophile. Suppose here you have benzyl chloride. So this carbon delta positive is electrophilic carbon. Okay, so this one can come here and this chlorine will leave. Okay, you can show that this one from here as well. See, this negative charge can come here and this can go there, and in that case this will leave. So in both the cases you will get the same product. Okay, and here the remember not to mention here the counter ion will be sodium. Okay, and here hydrogen gas will be released. Okay, so that will be gone. So those are not part of the actual reaction, so don't worry about that. Okay, you guys see? So what will be the product here? Then the product will be CH3 O, CH2, CH2, and then phenyl. Okay, see this one. So here what happened, that at alpha carbon, one of the hydrogens is substituted by a benzyl group. So that's why this is called alpha substitution. Okay, so in the book it's a generic thing given, so read that one. Okay, the last one is very important. The last one is carbonyl condensation. Carbonyl condensation. Okay, so carbonyl condensation means that let's say if you have this molecule, okay, cyclohexanone, and you take a strong base. So a strong base, what was the strong base in the previous slide we took? Sodium hydride. Here strong base is sodium hydroxide. So this reaction will be same. So what will happen that it will take one of the alpha hydrogen same. So the product will be here. This one as a sodium will be counter ion plus water will be the byproduct. Okay. Why this negative charge will form easily? Because it can be resonance stabilized with the carbon. So like this. Okay. So here this, remember this one is called enolate. Enolate. Okay. Enolate. So enol, negative charge, enolate. So if you don't take the electrophile, see this is, let's go back to the previous slide. Here is, this is the enolate. Exactly same thing up to here. There is no change. Here when we add an electrophile, it reacts with the electrophile. If you don't add any electrophile, then it will react with the another cyclohexanone molecule. Okay? And the reaction you can show with both, it can react here like this, or you can show with the enolate that the negative charge will come back and this will go here, this will go here. Both will give you the same product because those are the resonating structures. Okay, so what will be the product here? The product will be, I'm writing first this one. Okay, so is coming back the carbonyl, and this is making a bond with the carbonyl of another okay? And on this the OH is going back to this one, O minus. Okay, and this one will take a proton from water or in acid workup, and this will give you this product. Okay? So what is this compound? Alpha beta. If you take the carbon, so beta hydroxycarbonyl. Okay, so this is the beta hydroxycarbonyl compound. So that's what this is called condensation. Condensation means two similar molecules, this one here and this one here, two same molecules that condense together to make one product. Okay, so that's what this is called condensation. So these four reactions are very, very important. Okay, and then